In this video, I'll be talking about data sonification and applications to astronomical data. But first, I will give you an introduction to the various types of astronomical data to help you understand the data that we use and that is being sonified. And then I'll give you an introduction to some of the data sonification tools for two-dimensional type data. There are some tools for one-dimensional, two-dimensional, and time series, etc. I'll be focusing on two-dimensional data. And hopefully this will help lend insight to people who aren't astronomers to understand the data and how we are currently applying sonification to those data to help improve that, and then of course to help improve sonification in general for any kind of images, plots, etc. So first off, when you think of astronomy, you probably think of images, and that is indeed one of the types of data. So what I'm showing here is a wide field image of the sky taken with an instrument called the dark energy camera. And it's over a gigapixel in size, or gigapixel image. And there are, in this case, 60 different CCD detectors that are making this image. That's why you'll see a bunch of sections. But in this image, there are, depending on how long the image is taken, there are anywhere from several 100,000 to 1 million sources, objects there. So it's very sensitive, and there's a lot of information in there. Some of them are large galaxies, as can be seen by eye, but then there is many tiny things that you'd have to zoom in really deep to see. And usually those are the interesting objects. So what astronomers often do is exactly that. They'll use a wide field imager to find these rare or interesting objects and then zoom in on them to study them. And so if I were to zoom in on one, like this, what it appears, this is a galaxy. Actually, it's two galaxies merging. But that's really hard to tell from this image. What this image shows toward the center is just basically a blob of light with some sort of undefined form. But what you'll notice is that it's pixelated because we've zoomed in on this digital camera, and of course, then you'll see the pixelation as you get closer and closer. So most images that are studied are pixelated like this for objects that are distant. Also in this image, there are a couple other light sources. One is a star to the lower right, and then there's another galaxy to the lower left. So this is a very distant galaxy, which is very tiny on the sky, and that's why we have to zoom in and see it pixelated. Now, a similar galaxy, much closer to us, would appear like this one on the left I've just shown, and that's a beautiful image of it's two galaxies merging, just like this distant one, but it's in high resolution and color, etc., because not only is this much bigger because it's closer, but this image was taken with the Hubble Space Telescope, which is outside of the Earth's atmosphere. It's in orbit. The one on the right, which is the one I zoomed in on, and indeed the far larger image, is taken from a telescope on the ground. So we're looking through the atmosphere, and that tends to blur objects, especially tiny objects like this. So in short, we're looking at two-dimensional images that are pixelated, but in a way that's actually good for sonification, at least at this stage, because with sonification, you'll be able to hear the different pixels and get their values, and there's a reasonable number of them. Like in this case, there may be just 1,000 or so. Whereas if we were to try to sonify the left image, which is in high detail, that could get quite overwhelming unless you're doing things on a large scale. So what we also do is take those data, that image, for example, that small section of the image I was analyzing last time, and you would take that light and pass it through an instrument that acts like a prism. So it spreads out the light over a wavelength. And it does that. It spreads out that light, that white light, into the rainbow of colors and places it on a detector again, such that you have an image of the spectrum of that galaxy. And here you'll see a two-dimensional image, but it has streaks going through it. And one of them, which I've just highlighted, is that galaxy I showed you, but spread out across lengthwise horizontally. And what it's doing is dispersing it in its wavelengths. There's a brighter object at the bottom in here too, but in this particular case, we're looking at the center one. And if you were to take that image and those pixels and collapse them vertically, just down to a single horizontal line, and then plot that line, it would look like this. And this is a one-dimensional spectrum. So what this plot I'm showing has on the x-axis wavelength, and on the y-axis flux, which is the brightness. And so it's just plotting the brightness of the source for a given wavelength as you go through different wavelengths. So this is it's a one-dimensional spectrum, but if you plot it this way, you're actually plotting it as a two-dimensional plot, right? You have x-axis and y-axis. So you can analyze this in two ways. One, you could play the sound. If you're sonifying it, you play the sound stepping through wavelength in time, and then you would hear the change in flux if it's brighter or fainter per wavelength as you move along in time, which is moving along in wavelength. But if you could also decide to plot it in 2 dimensions, as it's shown on the screen, and display it in a 2-dimensional surface like your trackpad, and you can feel on there with your finger, for example, where the spectrum is and the shape of it and where it is brighter and fainter. Then we move to 3-dimensional spectra, and with certain instruments, we can take an image, as you saw, of that pixelated galaxy, but for each pixel, this particular type of instrument can get a spectrum for each one of those pixels. So you end up getting a 3-dimensional data cube. So it's an image, but each pixel has this 3rd dimension of the spectrum, or the brightness of that spot on the image for a given wavelength. Well, that might sound a little bit complicated or to conceive at first. One way to think about it is if you just collapse this data cube into 2 dimensions, you have an image, just a pixelated image. But if you wanted information for each spot, you could get that. An example of that is shown here. I have a 4-panel image shown, and on the left panel is a Hubble Space Telescope image of a very distant galaxy, so it's small and a little bit blurry, and it's a nice galaxy. It looks kind of like a pancake, I guess you could say, or a spiral galaxy that is at about a 45-degree angle, a little bit more. So there's this galaxy there, and then when we use this kind of spectrograph on it, we can create the next panel over to the right, second from the left, of that galaxy. And it's arbitrarily color-coded here. In this case, the red is brighter and the blue is fainter. So it picks up the light in these various pixels, and each one of these pixels has a spectrum. But one of the powers of this kind of spectroscopy is that if you go one panel more to the right, so a third from the left, you can see that this galaxy has sort of a rainbow of color. The pixels on the bottom are blue, and then they get more teal and green and yellow towards the middle, and then orange and red to the top. So there's this rainbow appearance. And what that is, in this particular case, is that each pixel is its spectrum. That spectrum for that pixel is, if it's moving away from us, it's color-coded red. And if it's moving toward us, it's color-coded blue. And, less toward us is more, if it's moving slower or less toward us, it would be green, and maybe less away from us, orange. So it goes through the rainbow of colors in how much it's moving away or toward us. And so in this case, the top of the galaxy is moving away from us, and the bottom is moving toward us. And you can interpret that if the color is analyzed, that it's rotating. This galaxy is rotating, and it's rotating with the top part of the galaxy going away and the bottom part coming toward us. So that's another bit of information you can learn using this kind of spectroscopy. And there are tools that we can use to analyze that. And you would want to find perhaps the axis in which it's rotating. And on that image, it's shown in pink in this case, but this is something that you can find out. Then there's time series data. And time series data is measuring objects as they change over time. What I'm showing here are a number of images of a nova explosion. And the bottom right shows a galaxy. It's a somewhat nearby galaxy. And in this tiny spot with the arrows pointing, there's a zoom in section of that. And if we look at each of these zoom in sections over 5 days, in the center, day 1, there's nothing there of note. And then day 2, potentially you see something, but by day 3, you start seeing some light showing up. By day 4, it's bright, and day 5, it's bright again. So something appears out of nowhere, and that's an interesting thing. This also happens for supernovae, which are much brighter than novae, and they are slower evolving. What you can do then is plot that light over time and on what's called a light curve. And a light curve has an x-axis with days, marking off the days in time. And on the y-axis is the brightness. In this case, it's called absolute magnitude. And so the object brightens with time and then fades. And you can plot those and make those curves. That's something that you can either play through sonification in time. So maybe each day is one fraction of a second or something like that. And you move through time and you can hear how the object brightens and fades. Or you can plot it in 2 dimensions as shown here and use some 2-dimensional format to listen to it moving around on the data plot. There are very fast bursts, things that occur in minutes. And here are examples of 2. On the left-hand side, there's a flare star. So it's a star that's there very faint, but then it bursts really bright. And on the right-hand side is another type of object that bursts a few times, but it takes a bit to show up here. And you'll see it burst a few times. And these occur over minutes to maybe hours. And so one of the challenges here is to try to catch these objects, to try to get information on them before they fade away. And here I'm showing a plot of a flare star, and the red arrows mean that it's not detected, and the blue squares is that it is detected. And what happens over time, and in this case about 40 minutes of time or a little more, is that the object brightens very dramatically within just a couple minutes and then fades slowly away. Well, if we wanted to get more information of this object, we would want a telescope with, say, a spectrograph to get a spectrum of it. But the challenge is these are rare, you don't know when they're going to happen or where. And so you use wide field telescopes like that first image I showed you to image the sky searching for these. And then once you find them, you have to you analyze the data, find them, and identify them. And then you can trigger another telescope somewhere else to move over and point to this one object, focus on that, and get a spectrum. But you have to do this quickly because, like in this case, you've got about 40 minutes. And so you'll have telescopes imaging the sky with a relatively fast cadence, and they find things, but you have to process the data and have people analyze the data within just a few minutes. And there are hundreds and thousands of these things to do, to then trigger a telescope to catch it before it fades. There's an urgency here, and so data sonification is very important because you want to analyze the images quickly and identify these objects very fast. And you want to use every means possible to do that and to verify your detections. Then there are the fastest bursts. These include gamma ray bursts, which last seconds to a few hundred seconds, and fast radio bursts, which last, they're as short as a millisecond. And although these things are very bright intrinsically, they come from across the universe and they're very faint when they reach the detectors. And so you have basically one shot at this. You get an image or a detection of them, and you want to do what you can to understand them or even detect and identify them. What I'm showing here are 9 separate images of a fast radio burst, and it's plotted on the y-axis, low to high frequency of the radio wavelengths, and on the x-axis, time, and each block is about a second long. But these bursts are about a millisecond long, and so they pass through, they arrive at Earth at the high frequencies first and then low frequencies over time. So when you sonify these data, and if you associate high frequency with high pitch in sound and low frequency to low, you'll hear the sound arrive first high and then it goes to low very quickly, and you'll hear a high to low chirp. One application for data sonification, which would be novel and is something to be worked on, is to detect these things using sonification because human hearing is quite extraordinary in picking up recognizable sounds in noise. This effect is called the cocktail party effect. I'm sure most of you have experienced that. If you're in a noisy room and you can pick up someone talking to you, or maybe everyone in the room is speaking another language, but a person is speaking your language, you can pick that up because it's recognizable. And so using this could be very powerful to help verify visually or with computer code detections. So I'm going to play a movie of these and see if you can hear these sounds, which can help visually detect these. Okay, so some of those were easier than others, but it just shows you how the noisy data sounds and what a signal is like through that. And lastly, in astronomy, data is plotted all sorts of ways, including scatter plots. Here, an example of 3 with the data either numbered or labeled or different symbols, or even just plain data points, as well as histograms, either just a plain histogram overlaid histograms or histograms with functions overlaid, as shown here, and even more complex plots that incorporate all those things and contours, etc. Okay, this is Vox Magellan. The display shows up on your desktop the size of your trackpad, and it also comes with a small toolbar window that has off for the sound, tone, and pulse. And for the display, if you want to show images, you go up to the upper tabs to Image menu, click on that and load first image.
Load image.
The tool has voiceover and can be navigated by keyboard commands. And this is a pie chart. So the first thing you might want to do is take your finger and move it around on the trackpad just all over to see where there's sound and where there isn't sound, so you get a sense of the shape of the object. So here I'm just kind of moving across back and forth on the trackpad, and this is feeling the edges. And now that I have a sense that it's a circle, I'll go to the top, which is at 12 o'clock. And this is red, and then green, and then orange, and then blue of the different pieces of pie. So this is 12 o'clock, and then 2 o'clock, and then about 5 o'clock, and about 8 o'clock, and back to 12 o'clock. And then I'm going to change from tone to pulse for a different sound effect. This is red and green, orange, blue, and back to red. Now this is just one. Vox Magellan can load up to 4 images. So go up to the image menu and load second image. And I'll load another image, so just the same pie chart again.
Load image.
And you can navigate between 1 and 2 images using the up and down arrows.
Displaying 1.
That's the down.
Displaying 2.
That's up. And so I'll just play the right pie chart now. And then over to the left. Okay, now I'm going to load an astronomical image.
Load image.
This will be an image of a galaxy. And if you remember earlier, I mentioned how we had 3D spectroscopy with those data cubes. This will be a galaxy that is a collapsed data cube, so it'll look like a pixelated image, and it'll have colors like the rainbow of colors. And we'll try to do a quick analysis. So there it is on the left. That's one of these galaxies in color. I'm going to go from I have two images right now to one.
Displaying one.
That's using the down arrow. And then the background is black, and the galaxy is sort of elliptical with a rainbow of colors, blue to red. And remember, blue is moving toward us and red is moving away. And the background black has no sound, but where the galaxy is, it does. So I'll pass my finger across, back and forth, try to find the galaxy. I'm just moving across the trackpad. Now that I know where the galaxy is, I'll say, okay, I'll make some cuts, because one of the objectives is to try to find the rotation axis, and that's where it goes from the bluest to the reddest. Okay, so the objective here is to go from blue to red, which would be low pitch to high pitch. And you'd want to hear the largest difference to find the rotational axis. So here's vertical. All right, here's horizontal. And here is going upper left to lower right. And here's upper right to lower left. And I think you can tell from the sound that it was upper left to lower right was the rotational axis. Vox Magellan accepts PNG, JPEG, and TIFF files, also properly formatted ASCII files. And it's possible in the future to extend this to include moving images and FITS files. So for PNG files, screenshot is easy. And so to give you an example of that, I'll hook over to Google Images, type in something like tree or something, and brings up a bunch of images of trees, green trees, pink trees actually, and cartoon trees. So let's just pick one of these. This looks good. This is a nice tree on a sunny day, a single tree on a hill with a blue sky and green grass. So we'll just make a screenshot. Maybe I'll try to avoid these little black circles here. Back and forth arrows on the browser. And screenshots appeared. So then we just go up to load image and
load
find
image.
the file that we just created. And there it is. And it digitizes it. So it takes a few seconds, and Vox Magellan has a 50 by 50 pixel resolution, so it will look pixelated. There it is. It's pixelated, but the bulk of the image is there. And right now we're listening to the blue sky. And so that tone is blue, and there's a little bit of a gradient in the sky, darker, higher up, and brighter or wider towards the horizon. And this is the leaves. The leaves on the tree sounds mottled, and that's the sky, and then the edges of the tree in the sky. And then we work down the trunk to the grass. This is the grass, and the grass is green like the leaves, so it has a similar sound as the leaves. That's the leaves, and that's the grass, a little smoother sound. And that's the horizon, grass to the sky. And then there's this dirt patch to one side, so we can hear that dirt is a different sound than the grass. That's the grass. And back to the dirt, which is kind of and that's the sky again. So finally, I'd like to show you how Vox Magellan handles scatter plots and multiple tones, where the multiple tones can indicate different properties. And so I'll open up Vox Magellan here.
On.
And I'll go to open up a data file.
Open data file.
And load a data set. Now this data set is just, it's actually for galaxies, but it's a scatter plot of data where they're all over the plot, but they're kind of mostly clustered to the right a little bit. And there are 3 different types of data here, colored green, blue, and red. Just there's some selection method there, and we're going to listen to these. They have assigned a different tone per data point. And so the green ones sound like bells, tubular bells here. That's them. And then the blue ones are this piano sound. There's no data over there. And then the red are like a wood block sound. So they're very different sounds. You can assign, many different sounds to them. But as you feel around on the trackpad, you can see there's like a lower density in one area, and then you'll feel and there's a higher density in others, and you can even feel where there are no data, like over here. And so this is a good way to understand where the data are. And then you can add a different tone, the second tone, this tone here, which would be assigned to some other property, so you can hear 2 properties at once. And if you move around different data point, you can tell that that's very different, and so you can understand how the data are different with 2 different properties at once, especially if you train yourself to that. It can be a very powerful way of analyzing your data. Another open source free tool is Afterglow Access, and I by no means am an expert at all. I've just only recently discovered it. Here's the website, and it's free. So if you just click on this, it'll load up. This is its dashboard, and it has the sample data set of FITS files. It handles FITS files. Here's the Eagle Nebula, which is a beautiful nebula. And if you scale it here, this is the image. And this tool does a lot of things. It's really helpful for astronomers. Here the image has, if you hit faint target, it'll highlight, it recontrasts it, so you can highlight some of the faint aspects of it, so that it brings out the nebula. But this tool does a lot of things like stacking data, measuring between data points, and photometry, all kinds of fun stuff that is really good for astronomy. But for here, we're going to use its sonification tool. And when it sonifies, it runs a horizontal bar from bottom to top, and it puts the different brightnesses to different pitches, as you'll hear. And it has a little tone at the start and at the end. So it sounds really nice, and here let's listen to it again. So from that, as it scans from top to bottom, you can hear what it sounds like. And in the sample data set, there are other things you can load. Here I'll load a globular cluster, which I think sounds pretty good. And so it's a way of sonifying your data, listening to how the different types of objects sound. That was a nebula. This is a globular cluster. Globular cluster is in the center of the image, and as it's sonified, it goes from the bottom to top again, and you'll hear it as it gets towards the center of the globular cluster. It's a really pretty sound. So again, this tool has a lot of aspects to it. You can invert the colors and even rescale the colors, and all kinds of things that you would do normally in like a DS9 tool or other tools for astronomy. So it's a really, really nice tool. Okay, so that was a quick summary of the different types of astronomical data, images, spectra, different types of spectra, time series data. We didn't touch on that too much with the tools, but you can imagine how that is. And then also these other plots like scatter plots and pie charts and etc. I do want to say that I've focused here largely on optical with a little bit of radio data, and in astronomy there are all the wavelengths: gamma ray, X-ray, UV, optical, infrared, millimeter, and radio. And for UV, optical, and infrared, those are pretty much as described here. They're going to be images or spectra, FITS files in formats that you've seen here. And high energy, which is gamma ray and X-ray, are a little bit different detectors, but some can form images like X-ray images. And with radio, it's also a little bit different format with receivers, but also you can form images. Thank you.